In this video, we will focus on the variation of the melting point of elements across period 2 and 3. In both periods, we can see that the melting points of elements follow the same trends. They first increase from group 1 to 3, then reach a maximum at group 4. Next, decrease sharply to group 5. Finally, reach a minimum at group 0. Note that in period 3, there is a slight increase in the melting point at sulfur, for the melting point of non-metal elements from phosphorus to argon. The melting point of elements is determined by the strength of interaction holding the particles together that is broken during melting. When explaining the variation of melting points of elements, we have to state the type of structure and the type of interaction holding the particle. Don't forget to mention whether the interaction is located between atoms or molecules. Lastly, always compare the strength of the interaction to compare the melting points. First, we see why the melting point increases from group 1 to 3. Elements from group 1 to 3 are metals with giant metallic structures, except boron is a semi-metal with a giant covalent structure. They have strong metallic bonds between metal ions and delocalized sea of electrons, so they have a relatively high melting point. From group 1 to group 3 metals, the number of delocalized electrons increases with the group number. Recall that group number equals the number of outermost shell electrons. With more delocalized electrons, the strength of the metallic bond increases as there is a stronger interaction between metal ions and a delocalized sea of electrons. The diagrams here show the metallic structure of group 1 to 3 metals. You can clearly see that as the group number increases, the number of delocalized electrons increases, and thus the strength of metallic bonding increases. Hence, in period 2, the melting point of beryllium is higher than that of lithium. In period 3, the melting point of aluminum is higher than that of magnesium, which is higher than that of sodium. Then, we see why the melting point reaches a maximum at group 4. Group 4 elements, carbon and silicon, have giant covalent structures. There are strong covalent bonds between atoms. Much more energy is needed to break a large number of covalent bonds in group 4 elements. The diagrams below show metal and giant covalent substance in solid and liquid states, respectively. When a metal melts, the metal ions become less closely packed. Weakened metallic bonds exist in liquid metals. This means metallic bonds are not broken substantially or completely during melting. On the other hand, when a giant covalent substance melts, the covalent bonds are completely broken. In conclusion, it takes more energy to completely break a large number of covalent bonds than only partially break metallic bonds. Hence, the melting point of group 4 element is the highest in a period. Next, we see why the melting point decreases sharply to group 5. Elements from group 5 to 0 have simple molecular structures. There is only weak van der Waals force between molecules, which is much weaker than covalent bonds between atoms for giant covalent substances in group 4. Hence, only a small amount of energy is needed to melt group 5 to 0 elements, and they have low melting points. Finally, we see why the melting points further decrease to a minimum to group 0. All group 5 to 0 elements are simple molecules with van der Waals force between molecules. The smaller the molecular size, the weaker the van der Waals force between molecules. As seen from the diagram, group 0 molecules are monatomic while group 5 to 7 molecules are polyatomic. The molecular size of group 0 molecules is smaller. Hence, the van der Waals force between group 0 molecules is the weakest. The melting point of group 0 elements is the lowest in a period. In period 2, the molecular size decreases from nitrogen, oxygen, fluorine, to neon. The strength of van der Waals force between molecule also decreases from nitrogen, oxygen, fluorine, to neon. Hence, the melting points keep decreasing from nitrogen, through oxygen and fluorine, to neon. In period 3, note that a sulfur molecule has 8 atoms. A phosphorus molecule has 4 atoms. A chlorine molecule has 2 atoms and an argon molecule has 1 atom. The molecular size decreases from sulfur, phosphorus, and chlorine to argon. The strength of van der Waals force between molecules also decreases from sulfur, phosphorus, chlorine to argon. Hence, the descending order of melting point for these elements is sulfur, phosphorus, chlorine, and argon. In explaining this trend, you should include the molecular formulae of these molecules in your answer. The variation of melting point of elements across period 2 and 3, with brief explanation, is summarized here.